Lagrange or Taylor Error Bound Part 1. Consider P sub n of x, often written as T sub n of x, or other letters, the nth degree polynomial approximation to a function f. For simplicity, let's look at P sub 2 of x, which is the second degree polynomial approximation to f. If we use this approximation for f of x, what happens to all of these other terms, f triple prime, the fourth derivative, etc., all the way out to infinity? We just totally ignore those, which means that we have an error in our approximation. And in fact, the error is exactly given by all of these left off terms. This error is also often called the remainder. So how can we find this error or remainder? Well, we don't really find the error or remainder. Instead, what we're going to look for is an upper bound on the error. That is a maximum possible error. How can we do this? Before I answer that question, let's do a little bit of algebra. And let's take our function, the exact function, and let's subtract off our approximation, which will give me f of x minus f of c minus f prime of c times x minus c minus f double prime of c times x minus c squared over 2 factorial. We'll put a plus sign right there, as if those terms still belonged. So what happens if I take f and subtract off my approximation? We'll look back up here. If I take f and subtract my approximation, I get exactly the error. So this, or this, whenever you see it, is another way of writing the error, also known as the remainder. Again, taking my actual function value and subtracting off these terms gives me everything left over. So how do we find this upper bound? Well, I'm going to try to convince you with my argument. That is, I'm going to do a simplified version of a specific case and assume that you can take that and go beyond to see that it works in all cases. For our simple case, let's assume that I know something about the third derivative of our function. First of all, that is positive. It doesn't have to be. We'll put absolute values on at the end. But also that it is bounded above by some value, some constant, as shown in the graph. Well, if this is true, if my derivative is bounded above by a value, then it's also true that when I take the integral of both sides, I maintain that inequality. Now I'm going to go through a few integrals. I'm not going to do all the proper notation just for the sake of time, and it gets really messy. I will start off the first one with proper notation, that is, if I were to take the integrals, I really should use a placeholder variable here, what I often call a dummy variable, which gives me that the integral from c to x of f triple prime of t dt is less than the integral from c to x of my number m times dt. Let's use the fundamental theorem of calculus to help us out. The integral of f triple prime is f double prime, plugging in the top limit, minus f double prime, plugging in the bottom limit, less than or equal to m times x minus c. I'll do the work right here. Antiderivative is m, some number, times t from c to x. Plug in the top limit minus plug in the bottom limit. And do a little bit of algebra to get what we want. But if this is true, my new inequality, then I should be able to take integrals again and maintain the inequality. So I won't put the placeholder variables in, we'll just talk through it. The integral of f double prime is f prime, plug in the top limit, minus f prime, plug in the bottom limit. So I took care of that antiderivative. Now minus, let's worry about the second piece. Well, f double prime of c is a number, so I can do the constant rule, f double prime of c times x minus c, much as I did this first integral over here. But that's less than or equal to my right side integral, which is constant rule m, and then a power rule, x minus c squared over 2. But if this is true, I should be able to do an integral again, and this is the last time we will need to do it. The integral of f prime of x is f, plug in the top limit, minus f plug in the bottom limit. So I took care of that piece. Let's worry about this next part. So minus f prime of c is a number. So we can do the constant rule, f prime of c times x minus c. Let's do that part. Minus constant rule, f double prime of c, which is a constant, and then a power rule, x minus c squared over 2. Looking at the right side integral, we get the constant rule, m over 2, times power rule, x minus c cubed over 3. But from above, what is this exactly equal? Well, it equals the error. And notice that I don't know what the error is, but I do know that it's less than or equal to m, which we saw was the max of my third derivative, times x minus c cubed over 2 times 3, that is over 3 factorial. So in general, the error or remainder using my nth degree polynomial approximation is less than or equal to, and I'll put absolute values here, the maximum of what? Well, the first left off derivative. Where? Well, on the interval from c to x. Most books put z here. I won't. I'll just leave it as x. Times what? Well, times x minus c to the first left off power, over that factorial. And this is called the Lagrange Error Bound. Sometimes called the Taylor series or Taylor polynomial error. Let's do one simple example of this. Suppose I know that f of 2 is 3, f prime of 2 is -1, f double prime of 2 is 4, and that the third derivative is bounded by 8. Using our second degree polynomial to approximate f, let's approximate f at 2.1 and find the maximum error associated with that approximation. So let's start writing our second degree polynomial, which is f of 2 plus, in this case, -1, f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared over 2 factorial. Which means that f of 2.1 is approximately 3 minus 2.1 minus 2 plus 4 over 2 factorial, or 2, times 2.1 minus 2 squared. But what is the maximum error using my second degree polynomial? Well, I know that it's less than or equal to the maximum of the first left off derivative times x minus c cubed over 3 factorial. And plugging in, I get 8 times 0.1 cubed over 3 factorial. Which is the maximum error associated with that approximation.